Hello, my name is Katie Morgan, and today I will be covering Case Connections 2. The first case that I am choosing to discuss is case number 2. This is answering and replying to the questions in order. So the first question that she asks is, I'm not sure I understand the issue. Can you explain how muscle glycogen is used normally during exercise? Glycogen is stored glucose, which can be stored either in the liver or in skeletal muscle for later use. The majority, up to 85% of the body's glycogen stores, can be found in muscle tissue. These stores vary throughout the day depending on the amount of carbohydrates you consume, the intensity that you're exercising, and the time since you exercised last. Interestingly, the use of glycogen in muscle cells prevents them from uptaking blood glucose. This is because the brain relies on blood glucose and cannot turn towards other sources of energy. Therefore, rather than depleting blood glucose, reducing the glucose that would be available for the brain, your muscles instead turn to their glycogen stores. During exercise, when your body needs ATP, glycogen stores are converted back into glucose, so that muscle cells can have more ATP. You can think of ATP as the energy currency of a cell, and it carries its energy in the form of phosphate molecules adjoined together. During exercise, a normal muscle cell would have phosphorylated glycogen phosphorylase, which should then convert glycogen into glucose 1-phosphate. Because it's phosphorylated, glucose 1-phosphate stays within the cell and is isomerized to glucose 6-phosphate, which can then enter glycolysis. Glycolysis is the first step of cellular metabolism and produces 2 net ATP per glucose molecule, as well as additional items that will then go on to produce even more ATP. Therefore, this is all to say that muscle glycogen in a normal cell is used to produce energy in the form of ATP. The second question is, I really like to take long walks. Will I still be able to do this with my friends? It should be safe to take long walks. When exercising, your muscle turns to different energy stores to continue exercise. Firstly, ATP is sourced from creatine phosphate because the associated phosphate can be donated to ADP, regenerating ATP for more energy. We see increased reliance on creatine kinase in individuals like you who lack glycogen phosphorylase because you are unable to rely on other processes, which I will now explain. The other two processes following this initial burst of energy include anaerobic and aerobic processes. The body turns towards anaerobic metabolism, or oxygen-independent breakdown of glucose first. This metabolism in general requires larger molecules that then break down into smaller molecules. When glucose is entering glycolysis, the energy-producing aspect of anaerobic respiration, it produces pyruvate, ATP, and NADH. When oxygen is available, the body then relies on aerobic metabolism, which uses oxygen to fully oxidize metabolic compounds and intermediates, creating significantly more ATP than anaerobic metabolism. While the body's preferred source of energy is glucose, it can also use sources of fuel such as fatty acids, which make up your stored fat, and amino acids, which make up your muscle. These processes continue to occur even without glycogen phosphorylase because they produce intermediates that are downstream where glycogen phosphorylase is active in cellular metabolism. Therefore, aerobic exercise can occur without glycolysis because glycolysis is the only aspect of cellular metabolism that is fully reliant on glucose and glycogen. In fact, we see individuals lacking glycogen phosphorylase have increased reliance on beta oxidation of fatty acids. Thus, while the initial minutes of exercise may be uncomfortable while your body is still utilizing anaerobic glycolysis, it will soon turn towards aerobic metabolism. Many individuals who lack functional glycogen phosphorylase experience what we call a second wind phenomena. Individuals are initially fatigued by exercise when you're utilizing anaerobic processes, but are then energized once more once their body relies on aerobic processes. The third question is, as a result of this deficiency, will I need to get up at night to maintain my blood glucose levels? Your body has other ways of producing energy without relying on glycogen stores. Firstly, your body will use up the blood glucose found from your last meal. Your body is able to use the glucose consumed before it is still stored as glycogen, so free glucose should sustain you for a few hours until you fall asleep. Then, while you are asleep, your body will turn towards other sources such as fats and amino acids, as I just mentioned in the previous question. However, if you would like, providing your body with free glucose by having a small snack at night would not be harmful if you're unable to sleep. The next question is, do I need to worry about producing excessive lactate during intense anaerobic activity? No, you should not worry about excess lactate production when exercising anaerobically. In healthy individuals, anaerobic exercise relies predominantly on glucose, and depleted blood glucose may be replenished by breaking down glycogen. In glycolysis, glucose is then converted to pyruvate, which is then converted to lactate so that NAD+ may be regenerated and used again in glycolysis. Because individuals like yourself do not have glycogen phosphorylase and cannot replenish glucose by breaking down glycogen stores, anaerobic glycolysis does not have the same opportunity to provide the intermediates as aerobic metabolism does. You will not have the same increase in lactate production because you will not have the same reliance on glucose breakdown. Further, individuals who lack phosphate dehydrogenase actually increase their lactate metabolism because lactate can be used to produce glycogen, the same product of glycolysis. Individuals who lack glycogen phosphorylase, however, often experience an increase in creatine kinase metabolism. Large-scale increases in creatine kinase may explain the muscle fatigue, cramping, and pain observed when you initially take in anaerobic exercise, as well as the associated darkened urine present in most patients. Therefore, while anaerobic activity may not cause lactic acidosis, you should be conscious of the stress this exercise places on your body. This concludes our discussion of case 2, and I will now move on to case 4. In case 4, the baby most likely has glycogen storage disease. In healthy individuals, blood glucose remains elevated for the first few hours and is then stored in the body as glycogen. These glycogen stores are then subsequently broken down for energy and can increase blood glucose up to 20 hours after eating. However, glucose is not the only form of energy that is consumed, and other energy sources can be used to create glucose and glycogen. One such substance is galactose, which is ingested as lactose and composed of glucose and galactose. This is the primary source of energy for our case study 2-month-old who is consuming breast milk. In the baby, the galactose is phosphorylated by galactokinase, producing galactose-1-phosphate. Galactose-1-phosphate uridine transferase then aids in the conversion of galactose-1-phosphate into UDP-GLC. UDP-GLC may then be converted into glycogen for storage or into further processes to produce glucose. An inability to use your stored glycogen, the intermediate produced prior to glucose release, would explain why the baby gets irritated 2 hours after eating. While blood glucose is high, the baby is satisfied, but once glucose begins to drop, the baby is not able to release glucose, which is stored as glycogen, and blood glucose falls, upsetting the infant. Further, the baby's presented symptoms align with those often seen in glycogen storage disease. Individuals typically arrive hypoglycemic and display hepatomegaly, or an enlarged liver. Further, in healthy individuals, epinephrine should stimulate the conversion of glycogen into glucose, but this does not occur in individuals with glycogen storage disease, explaining why there is no increase in blood glucose following epinephrine administration. It is also unlikely that the baby is suffering from the other diseases. Hereditary fructose intolerance is unlikely because the baby is only consuming breast milk, which has minimal fructose, which would be used in fructose intolerance. It is also unlikely that the baby has galactosemia because blood glucose increases following breast milk consumption, so the baby is initially properly metabolizing galactose. Lastly, glucose 6-phosphate dehydrogenase is used in the pentose phosphate pathway, which is integral for cellular metabolism in red blood cells. Without functioning glucose 6-phosphate dehydrogenase, the red blood cells would undergo hemolysis due to the accumulation of reactive oxygen species. Since the baby appears to have normal blood, as laboratory results were normal other than hypoglycemia, glucose 6-phosphate dehydrogenase deficiency is unlikely. Thus, from the presented list, glycogen storage disease is the most likely cause for the baby's symptoms.